say that we claim that gamma is least upper bound for E. Okay, that's what my claim is. Okay, so what is the first property that gamma should satisfy? That every element in E must be smaller than gamma. Okay, so we need to show first. We need to show that what? That every alpha, so it's like alpha is smaller than gamma for all, okay, so
For all
Alpha belongs to E.
for all alpha in E. So that's what we want to show. Okay? How are we going to show that? Yeah. So what this first part is going to show, that this gamma is really an upper bound for E actually. Okay? So how should we show that? I would like to prove this property first. Okay? You forget about the second thing. I would like to show this property. We'll pick an element from alpha and then. So first of all, we need to reflect upon what is the meaning of comparing a cut with another cut. Okay, so you're gonna say that take arbitrary. So it's like arbitrary alpha from E. Okay, alpha is smaller than gamma. Now alpha is smaller than gamma if and only if alpha is contained in properly
contained
in gamma. Okay? So how should I show it? So in other words, I need to verify this factor. That is going to show the properness actually. But we need to show the subsetness as well.
Is it necessary to show this for converse as well? We just show alpha is subset of, and hence we apply the definition it will imply for the less.
Exactly. So what we need to do, let P is some point in alpha. Okay? And why this point should be in gamma? And why alpha is a subset of gamma? Because it's a union actually. So in other words, I mean, if you wish, you can give a direct argument like this is true. This is true. This is true because alpha is contained in the union of all alphas which are in.
So alpha is
alpha is contained in all of the union, and this union is gamma. So like the first property is pretty much obvious. It is obvious, but as I said, this course is about proving obvious things. Nothing is obvious, it's basically something that we have learned that, oh, that's obviously true, we have to justify it, basically. Okay? Oh, you can show actually that why this is a proper subset. Why this should be a proper subset. And why this should be the case. What if E is singleton? You can have the case actually. In that case, you don't have.
There is singleton occurred.
Then is singleton occur. So point the reflector form. So you can't have that basically. Okay. No, I mean okay. Alright. I mean we are talking about the singletonness of E actually. So we're not saying that cut is basically singleton.
So there should be
There's just one cut, you mean? In E.
So in other words, think through this that why this should be non-trivial. Okay? Let's move to second. You must have some points to reflect upon. So what for the second property, what should we do? What should we do? What's the second property?
Sir?
Let's think through the second property.
Sir?
If there is another upper bound, then this upper bound is smaller than
Okay, that's one way to do it. That if there is another upper bound, then this upper bound must be smaller than that. But you have another recipe to do that. And what is that?
If anything is less than this thing, then
Exactly. So if anything is smaller than this thing, this gamma, then it can't be an upper bound for. Yeah.
Sir? In the previous property that we verified, it should be improper subset as well, because alpha should be less than or equal to gamma.
Okay. Less than or
Equal to.
less than or equal to.
yes, sir, upper bound.
Okay, just think about it. I'm leaving this to reflect upon that. What should we do? At the moment we have just this definition of order. Are you going to verify?
Okay.
Okay. Okay, so what should be the second property? So for the second property we need to say that let I have some beta, though, but like we have reserved beta for upper bound, so we need to say something sad. So let's take a delta, okay, and it's smaller than gamma. We claim that delta is not upper bound for E. Why should this be the case? So what does this delta is giving to you? This relation is giving to you what? So this implies as a delta is we need to prove that gamma is supremum for E. Okay, you can't.
delta is subset of it.
Okay, so as delta is a gamma, so delta must be a properly contained subset of gamma, which is union of alpha,
As in E.
alphas in E such that alpha, so union of all. So if this guy is properly contained in gamma, what does it mean?
It means
There
there
is
is
an element
in the union,
not a,
which is not in delta.
not a
Right? So in other words, so as the delta is properly contained, so it's not delta is not equal to gamma. Okay, so it's like there are elements here which are not here actually. So let P is an element in gamma such that P is not in alpha, not in delta. So what should I do? So what does this tells me? Basically, so if P is in gamma where it should be,
In some alpha,
is an E.
okay? If the P is in alpha,
some alpha, and it is not in delta,
okay?
that implies that it's not in upper bound.
So let's think through it.
Delta is
So if the P is in gamma, so as P is in gamma, so P must be in alpha for some alpha in E. Okay? So if P is in alpha, for some alpha is in E, and P is not in delta, then what conclusions you can make from here?
Yeah, it's not.
What conclusions you can make from here? Can alpha be a subset of delta? If we have something, so P is in alpha and P is not in delta. So can alpha be a subset of delta? Properly. But you know, again we are saying we need to show that that's something smaller than gamma is not a upper bound. And for if something is not upper bound, what do you need to show? We need to show that there is an element in ordered set which is not satisfying this relationship. Okay, so which is not smaller than delta. So if P is not in delta and P is in alpha, so we say that alpha is not contained in delta, obviously. Okay? If alpha is not contained in delta. Is it possible that alpha is contained in delta, but there is an element here which is not here? It doesn't make sense. Okay? So if alpha is not contained in delta, what does it show? So alpha is not less than delta. And if it is not less than delta, thus delta is not upper bound for E. And these are proofs. Okay? We need to play through the definition. Something which is making sense? So writing a precise argument, no matter how small detail you need to give, try to write as much as details in this first course actually. Or if you are writing in a compact form, then it should be convincing. Okay? There shouldn't be hidden details actually. As you learned in mathematical thinking that your reader should feel easy rather than he need to use his mathematical skills to interpret your things. Okay? So imagine that the other side doesn't know mathematics and you are basically convincing with your arguments. Okay? So delta is basically a cut smaller than gamma. And we are saying, if you recall the definition of least upper bound, the second property says that if you want to prove something to be an least upper bound, okay, say gamma, the first thing is that it should be an upper bound. That's what we showed. And second thing is that we need to show that if you take something smaller than gamma, then it can't be an upper bound actually. So we shown that we picked that delta which is smaller than gamma, and we shown that there is alpha in E which is not smaller than this delta, and hence this delta cannot be an upper bound for E. So if something is smaller than gamma, that cannot be an upper bound for E. So this is going to show that E is the smallest upper bound basically. So anything smaller than that cannot be an upper bound. So it's the smallest upper bound basically. Okay? So that's what we need to show. Alright. So we prove the least upper bound property. So now you have to think analogously for greatest lower bound property. Try to write that proof. This will be important actually. Maybe it could be one of the problems in the exercise sheet actually. Okay? So what should we So what is remaining now in the meta theorem? What is remaining now in the meta theorem? What is the key thing which is remaining now? So we've shown that R is ordered field. We've shown that R has least upper bound property.
R is extended.
Okay, we can also show that R is the only ordered field with such a property. There can't be any other ordered field with such a. Yes, we need to show that R extends Q. And what do you mean by that? In other words, Q is sitting within R. So it's like if that's my R, okay, then Q is, sitting here within R as a subfield, okay, and it's playing nicely with the addition and multiplication and order on R. Okay, so it preserves all three operations actually. That's what we want to prove. Okay, so we have already shown basically something similar in case of Z actually. So Z was embedded in Q, but not as a subfield, but it's embedded in Q actually basically. So it's kind of a Q extended Z. Okay, but the good thing is that Q has a structure of field. Okay, and it is sitting inside R. So what should be, so there we define projection or maybe an embedding. So what precisely I would like to do is basically to show that Q can be embedded,
Sitting silently.
okay, in R. Okay?
Yes, sir.
That's what I would like to show. So for that I need to do what?
You should define an injection.
So we need to define a map basically.
Left from.
Okay, we need to define a canonical map. So what do you think that if you pick a rational number, what would be the corresponding cut corresponding to that rational number? So it's like you have a rational number and you want to find a corresponding cut there. I'll tell you later that what we have just done actually with respect to least upper bound property. Actually what we have done is we have filled the gaps. So now I'm going to show that there are no gaps that we had previously. I'm going to show that later, but at the moment just think about it. I would like to define a map, for example a canonical map pi from Q into R. So if I take a rational number
X.
R, okay, from Q, then what do you think that what should be the cut corresponding?
All those elements in Q which are less than 1.
A cut with supremum R.
Cut with supremum R. So the first question is, do cuts going to have a supremum? Have we proved it that the cuts are going to have a supremum?
But that's supremum.
Okay. Is this something that we have?
Define all those elements which are less than R.
But is this an illegitimate question? It might be something. Can we think about supremum for a cut?
Yes, sir.
Yes, sir.
So what should be that supremum?
That supremum will
We
also,
always have a supremum.
will also be a cut.
It's a good point to reflect upon. Okay, so tell me the cut corresponding to any picked rational number. And you need to keep this thing in hand that Q has a different structure. There you have a classes, so it's a class corresponding to equivalence relation that we do previously.
And
Okay, so
then,
what should be the cut corresponding to this? So how about thinking that R star? So it's like for every R, you have a cut R star.
define R
Okay.
star. Now we define R star.
So the R star, okay, R star means, what's your guess? Comprises of those elements of Q such that less than R, so it's like a very natural candidate. Okay?
सर हम ये मतलब थ्योरम ही कंटिन्यू कर रहे हैं जो चीज़ है फिर क्या चीज़ ये शो कर रही है?
We are showing that, R extends Q, that part. Okay? That R, so if we have defined a new structure R, we haven't lost Q actually. Q is there actually. So we are going to show that within R, there is a photocopy or a copy of a Q actually. Okay? We need to explicitly write it that we haven't lost it.
Sir, so Q preserves some of the structures, it does not preserve its least upper bound property.
Yes, obviously.
So there are things that
Obviously. Therefore you constructed basically R. I mean if the Q has the least upper bound property, you wouldn't have a problem actually. We should be able to solve that equation x square equal to 2. Okay? But we know that there is no rational solution there.
And we also have a confusion that can we call Q as a subset of R?
Can we call
Q as a subset of R.
Q as a subset of R? Okay. So we can call it because actually we are showing this actually. So we are not going to say that this Q which has a different structure is a subset of R, but we are going to show that there is something which exactly looks like Q, which has all properties of Q, and it's a subset of R. So that's what we are going to show. So the first thing, so whenever we define a map, the first thing that we need to show is what?
Well defined.
Is it well defined? Okay. And in order to show that it's well defined, what we should think about? Existence and uniqueness. So existence and uniqueness. First, I told you this, but like you need to tell me precisely. So we need to prove that for every element in Q, there must be a element in R which should be a cut actually. Okay? And that cut must be unique. So you can't have that one R is related with two elements in R. So the first thing is that to verify that is R star a cut. And then second thing that we need to verify is that is R star unique actually. Then pi would be a function. Okay? So is R star a cut? Do you think that it has all properties of cut? Okay. Is it everything?
No, sir.
No. There are rational numbers which are bigger than R. Is it empty?
No, sir.
There are rational numbers which must be smaller than R. Okay? Is it closed downward? So in other words, you take a P from R star, okay, and you take any other rational number which is smaller than P, but since P is smaller than R, then that rational number must be smaller than R.
It should be a rock star.
Hence it must be.
Rock star.
So the first thing to check would be is R star a cut? Okay? So you need to write this proof for yourself. Not difficult, very easy to follow. You need to think about that. So the second thing that we need to show, what you call the uniqueness. So existence problem is solved actually. We actually, when you think that existence uniqueness, what do you mean by that? For every element in Q, there exists an element in R star which can be kind of an image of basically which can be treated. For example, if I take R from Q, then there must be a cut here which corresponds to it. Okay, so we've shown actually that yes, we do have a cut. Okay?
So we do it like we take two elements from Q, equal elements, and we show that images are also equal.
So now we need to show the uniqueness. Okay? So you see, we are defining things, but we are justifying them. Okay, I'm not. You need to be very careful about your argument. So in order to show that this pi is a legitimate map, the last thing that we need to show is that how you prove that something is 1, 1?
Take image is equal, show that inputs are equal.
We need to show that if
outputs are
outputs are equal, then
If phi of r is equal to phi of t, then r should be
I expect more sophisticated statement. Okay? It's not outputs and inputs, we need to show that if we have two images, they are equal, then the pre-images must be equal. Right?
So what you're proving, sir?
Huh?
This proof would be what injection.
No, no, no.
Yes, sir.
Oh, sorry, this would prove injection actually.
injection.
We need to also do that, because we need to first show that it should be.
For any pre-image, there is a unique
Okay.
image.
So you need to take that, let R and S are 2 points in Q such that
R is equal to
R equal to S. So why do you think that their corresponding cuts must be equal? So what would be the cut corresponding to R?
Less than R.
So it is going to be P, those P for which P is less than R.
Now simply replace R with S.
But since R is equal to S, in it, then this set should be P belongs to Q such that P is less than S. Why? Because R is S. So if it is equal to S, then what is this?
S star.
That's S star.
So that's right.
So it's like it was a trivial proof, okay, something very simple, but worth reflecting upon. That if you take two elements which are equal, then their corresponding cuts must be equal by this definition. Okay? And this is going to show that our map is really a map actually. Okay? It's a function. Okay? So what we should do next? So we proved that pi is well defined. So what is definition of embedding? That when I'm saying that Q is embedded into R, what we need to do? What is definition of embedding? Q? Okay, that's okay. That's my non-technical way to say this statement, but I'm expecting a mathematical answer.
It will
So
follow
something is
properly.
embedding if it is injection, and it respects basically the structure, okay, of for example in this case R. Okay. So in other words, I would say that pi is embedding. So pi is embedding if what should happen? What are the properties that we should verify? If pi is embedding, if pi is 1, 1, okay? It's a 1, 1 map. Not 1 to 1, I'm not talking about on to, not bijection, just 1 1. Okay, so R contains at least as many as points as Q actually. Okay? And what should be the second thing? That it should preserve the structure of R. In other words, addition, multiplication, and order. And what do you mean by that? That if I have pi of a sum of two rational numbers, then it should be same as pi of R plus pi of S, okay? And what should be the third property? Okay, it depends on the structure actually, that the structure has how many operations. So the properties can go up and down, okay? If the set has only one operation, then you'll have just one. Okay, so what do you need to do? Pi of RS should be equal to what? Pi of R and pi of S. Okay? Actually, you will not find this pi symbol in Rudin, okay? So it's something that I'm writing it explicitly. I guess that Rudin is not even discussing this explicitly. We're just saying that, okay, it's obviously true. Nothing is obvious for us. Verify things. Okay, so what should be the fourth property? Is it all? We should have. So order must be preserved. In other words, if R is a rational number which is smaller than S, then pi of R should be less than pi of